Hi everyone, what's up? Today I want to show you a very interesting problem in multivariable calculus. And it's a really simple one too, and the final conclusion that we'll get to is going to be really insightful. So yeah, let's do it. So say you have a box and you want to find out if you change the dimensions of the box by the same magnitude, what dimension will create the biggest change in the volume of the box. Okay, that is the summary of this question up here. To changes in what dimension is the volume of a box most sensitive to, okay? And here I just simply picked an arbitrary length for each dimension. And we're gonna use calculus to solve this, and it's gonna be really simple, really easy and kind of fundamental calculus, okay? It's not gonna be anything crazy. So if you want to approach this problem, I think there may be other methods, but the easiest one is to use the approximation formula, okay? So there's a formula that goes, I'm going to give you the formula using volume and LW and H notation. I think that would be appropriate. So this formula says that the change in any variable, in this case, our variable is going to be volume, because we're interested in finding out the volume. The change in any variable is going to be approximately the same as you have the partial derivative of this variable with respect to one of its inputs, and I was gonna say partial x, but really this is gonna be partial, let's say L, and then you're going to evaluate this partial derivative at a specific point L naught, W naught, and H naught, and then you're going to multiply this by delta L, okay? And you're going to write this term for each input variable that you have, okay? So in this case, we also, besides L, we also have W and H. So I'm gonna write this same term, but by differentiating with respect to W and H. So that will look something like this. Partial V, partial W evaluated at L naught, W naught, and H naught, and then this multiplied by a change in W plus, again, very similar, partial V, partial, and now we just have height, and again we evaluate this at L naught, W naught, and H naught, and we multiply by a change in height, okay? So over here we have every element or every ingredient that we need to get to a conclusion for this question. So we have a change in volume, we have changes in each of the dimensions, and then we're gonna look at what these partial derivatives are gonna give us, what numbers they're gonna give us. Because think about it, when you evaluate these derivatives, you're just gonna get a number, you're gonna get a coefficient. And if you, based on that coefficient, you can think, okay, well, if I increase all the dimensions by 0.1 units, then whatever dimension has the greatest coefficient will create the greatest change in volume, okay? That is the reasoning we will use. So first of all, let's compute these partial derivatives and evaluate them. So we're gonna have the partial derivative of volume with respect to the length. That's gonna be really easy. I assume you already know that volume is just gonna be the length times the width times the height, but I'm just gonna write it out. So if we differentiate this with respect to L, we just get WH, and that means that our derivatives, so I'm gonna write all the derivatives down here and then I will evaluate them. And then if we do partial, the next one is W, this we know will be equal to L times height, and then partial V, partial height, we know that will be equal to L times W, okay? So now I don't know if it's intuitive or not, but when I use L naught, W naught, and H naught notation, this set of points or this set of values are gonna be these numbers up here, okay? I assume that would be intuitive, when you approximate, usually you pick a reference point, and the reference point in this case, well, it's just gonna be the current volume or the current dimensions of the box, and the current dimensions are gonna be this up here, okay? So I didn't say that L naught W, L, this set of points here, I didn't explicitly say that they correspond to this, but hopefully that's something that you could infer by yourself. I think, yeah, it's probably very intuitive. So yeah, now let's continue. So we're gonna say that a change in volume will be approximately the same as, so now we have this derivative evaluated at the point that we're interested in. So now we have W and H, 4 times 1, that's just gonna be 4. We have 4 times delta length, okay? Now, what about this derivative? Well, this derivative is going to be this expression. So you have 3 times 1, that's going to be 3. So plus 3 times a change in the width. And now let's see the last coefficient that we get for the height. Now this is going to be interesting, and the answer we're going to get may seem kind of counterintuitive. If you have this function here, you have this partial derivative, you're going to get this number here, so you will do L times W, there's going to be 12. You have 12 times a change in the height. Now, how can you interpret this? Well, as I said before, the dimension with the greatest coefficient will create the greatest change in volume, or will be the cause of the greatest delta V. Now, the height, even though it's the smallest dimension, the height is going to be the dimension with the greatest coefficient, okay? And that's going to be really interesting because, you know, I think the only way you can reason why this is the case is by looking at a box. Really, if you look at a box with these dimensions, the length equals 3, W equals 4, and height equals 1, you're going to see that if you increase the height, you're going to create the box, the L and W, they will remain the same, but you will increase the height over a very long area, okay? That area is going to be 3 times 4. You're going to increase the height over a very long space, a very large region. And since it's a very large region, well, a very small increment in the height will give you a very great, a really large change in the volume. I guess, hopefully, I'm assuming, yeah, I will post a picture now of what I'm describing right now. I think that's a really nice way to visualize what I'm saying. But yeah, usually in these types of problems where you have a geometric, you have pretty much any shape that behaves well and that you can find its volume relatively easy by just having a couple of dimensions, it will happen, I think in most cases, that the dimension with the smallest magnitude will always be the dimension that creates the greatest change in the volume. And I would guess probably in the area too of a shape. Let's actually do that problem real quick, yeah. What if we say, yeah, I did not plan this for this video, but what if you have a square, what if you have a rectangle, you have a rectangle. I'm going to use different, say you have the following rectangle, so you have something like this. I'm going to call this A and B. We know the area is just simply going to be A times B. Therefore, a change in the area will be approximately the same as, so partial big A, partial A, that's just going to be B. And I'm just going to say this is 1 and this is 4. Yeah, let's do this problem real quick because now I'm interested in, I know this works for volume, but what about for area? Well, let's do that real quick. So I'm gonna use this notation really. So the partial derivative of A with respect to small a, we know that's just gonna be B, which is just gonna be 4, and the partial derivative of big A with respect to B is gonna be A, which is just gonna be 1, and therefore the approximation formula will look, so we have A, this is gonna be 4 times a change in the width, which I denoted by A, and then we have times, yeah, indeed, yeah, so this works out actually. Oh wait, what? Oh yeah, we have this, so 1 times, which is really changing B. So the idea that the smallest dimension will give you the greatest change in volume, and now I'm sure that it will also be the case in area. Notice that in an area problem, notice that here the greatest change in the area will be caused by a change in A, which is the smallest dimension of this rectangle. So yeah, this reasoning of the smallest dimension creating the greatest change works for volumes and areas, okay? I didn't think of areas, but now well, we just did it here real quick. So that's very nice. Hopefully this is insightful. Hopefully you find this interesting. I think it's really nice. Very counterintuitive. So yeah, that's nice. Yeah, so this has been the entire video. Hopefully you learned something from this, and I hope to see you in the following video. Bye.